Welcome my dear little friends, my students. I am back again. Today we are going to learn a little more about distance and displacement. So this video can be called the extension of the previous video in which we have learned distance and displacement. Watch till end because you have a surprise at the end. In that video, we have learned distance. Displacement too, we have learned. Let us recapitulate the terms before going into the next part. Distance is said to be the entire length of the path, be it rectilinear or curvilinear. Let us take this example of a curvilinear path. Suppose an object starts from this point and reaches that point. If we could measure the length of the path by any measuring tool, the length would be the distance. But the displacement will be shown by this straight line. Nothing else than this line is the shortest length of the path. It is clear from the graphics that the length of this straight line is much less than that of the entire path. I am showing the direction of the displacement by this arrow. Now let us take an example of a semicircle. Suppose this is the semicircular path. A man walks along the circumference of this semicircular path. He starts from the point A. After some time, he reaches point B, which is exactly opposite in position to A. The distance is the entire length of the circumference from A to B. But what about the displacement? Certainly, the displacement is a straight line drawn from A to B. Remember that this straight line must be passing through the center of the semicircle, as these 2 points are exactly opposite to each other on the circumference. I am showing this line by the mouse pointer. Therefore, the straight line is the diameter of the semicircle. In other words, the diameter in such a case actually represents the displacement. We can tell the measure of displacement if we know the length of the diameter. Its direction is from A to B, as is shown by the arrow. We have discussed distance and displacement in a curvilinear path. Look, with this discussion, we have come to know that distance is always greater than displacement if the path is curved or the object continuously changes its direction. What happens if the path is rectilinear or absolutely straight? Let us take the following example. In this example, a ball is found on the floor. If you push the ball to its right side, it will start rolling down the floor. Is there any doubt about it? No. What happens if the ball keeps rolling? You might say, sir, the ball may come to stop after covering a certain distance. Right you are. But what if you push the ball harder? It will definitely move towards the right side wall, strike it, and come back. Here, you have to assume that the ball is experiencing no other external force than that exerted by you. I mean to say that nothing should stop the ball or change its direction. In that case, the ball will be moving through the edge of the tiles. I mean, the straight line shown in the diagram. In this case, the ball will be said to be having rectilinear motion. Look, the ball starts from here. It stops at this position. There is a difference between the initial or the starting position and the stopping or the final position. Therefore, at position 2, the distance and the displacement are same. If it stops at position 3, the distance is this much. The displacement is also same. Same is the case at position 4 too. You will get the same result at every position along this straight line. So we can conclude that distance and displacement are equal in rectilinear motion. This is another point of distinction between distance and displacement. Remember, both the distance and the displacement are maximum when the ball strikes the wall. Also, they are same. Look at the graphics. After striking the wall, the ball is coming back to the starting position. Look, the total path covered by it is increasing. If we measure the length of the path described by the arrows and add the lengths, we get the distance. But displacement? See, the ball comes back to position 4 and stops. Measure the length between the initial and this position, as this is the final position now. This length, I am showing by this arrow, is the displacement. Displacement decreases as compared to its maximum value. Again, the distance increases if the ball stops at position 3, but the displacement still decreases. Therefore, it is clear that the distance goes on increasing, but the displacement goes on decreasing till the ball comes back to the original position. You know that at the original position, displacement is 0, as there is no difference between the initial and the final position. So, this is another point of distinction which says that distance can never be 0, but displacement can be. What happens if the ball still moves? Or if you don't stop it? Or if nothing stops it? Or if nothing changes its direction? If it moves along the same straight line, but in the opposite direction from the original position, don't worry. Just say that the direction is negative in this case. Negative implies opposite here in this case. If you consider the rightward direction positive, simply call the leftward direction negative. Yes, as simple as that. Or if you denote the leftward direction positive, call the rightward direction negative. It's up to you, it's up to the ongoing situation. So, another point of distinction is that distance is never negative, but displacement can be. Let me add one more point. Distance does not need any direction, but displacement does. Therefore, distance is a scalar quantity, but displacement is a vector quantity. We are at the end of the video. Now it's the time to reveal the surprise I mentioned at the beginning of the video. The surprise is a request to you. Write this distinction in a tabular form. Thank you.